Okay, hello everyone. So we are moving on to a new topic, buoyancy and Archimedes principle. So let's see what is buoyancy is. I believe you guys have an idea what is buoyancy means. If something is floating, um, we say that there's a buoyancy force or a buoyant force acting on it to lift it, like keep it floating on the liquid. Say for an example, let's say here's a lake and here's the fish one more time, and okay, a boat is floating. So when things floating, they don't completely stay above the water surface, always some amount is under the water. So this thing is floating, so this is the boat. So floating means its weight W is being supported by something. That something is being provided by the surrounding liquid, in this case water, is pushing back on it, right? This is called the buoyant force. So sometimes we mark it as BF, sometimes FB, either way, buoyant force. So even you might have experienced this, like let's say you are standing in water in a swimming pool. So here's the water level, here's the bottom of the swimming pool, this is you, part of your body is underwater, and you might have experienced this, that you feel little lighter when you are underwater, when you are standing inside water. If you wanna, let's say this is a shallow river and there's a big rock underwater, you want to lift this thing. Again, it feels lighter while it's inside water, but the moment it comes above the water, you feel it's heavier. Actually, you feel the real weight of the thing, because while it's underwater, there is something pushing on it. That's called the buoyant force. So that's the idea of buoyancy, right? So where is this coming from, or how do we calculate this? How do we figure out the math? So that's what we're gonna talk about now. So we're gonna do a little experiment. So this is what we do. Let's say we have some mass, right? So this is some mass, couple of grams. So we're gonna weigh it. We're gonna take a spring scale. Here's the spring scale. Attach it like this using a string. And we're gonna weigh it. So let's say when you weigh it, it reads m kilograms, and so you know the weight is gonna be mg, right? So this is just outside the water while it's in atmosphere. You're gonna measure it, and then we're gonna lower it into, so let's say the scale reading is right here. Then you're gonna lower it, so we have the scale. Here's this thing, the hanging mass, and then we're going to lower it into a beaker of some liquid, let's say water. We said that we submerge this in a fluid. Submerge. Or sometimes we use the word immerse. So we submerge this in the fluid. Now we see that the scale reading decreases, it goes up a little bit, so it's right here. So inside water, what it reads is something little less, let's say m1 kilograms. Or the weight, we can say the new weight. The better word is apparent weight. I think this is how you write it. Apparent weight is m1g, right? So the weight decreases a little bit, the scale goes up a little bit. What's the difference? This weight, its original weight, let's say W0 minus W apparent, the new artificial or kind of fake weight we measure inside the liquid, inside the water, that's apparent weight. When you take the difference, that is buoyant force. Water is pushing back on this thing. When you insert this object into the water, some water needs to, like earlier you had this empty, not empty, the container with some water level, right? Now when you insert this mass into the container, into the water level needs to go up, giving space into this new object, right? So that water level that rises, it is actually pushing back. So it's pushing back on this thing. That's called buoyant force. It comes from, actually mathematically we can show that it comes from the pressure difference between the top and the bottom of this object. You know that at different heights, different depths, the pressure changes. So likewise you have low pressure at the top, high pressure at the bottom. So that pressure difference creates this force on the area of this object. So we don't have to go into all these details. In simple terms, you have this actual weight, or the weight outside the liquid, and the weight inside the liquid, or the apparent weight. You get the difference, that's your buoyant force. Okay, so now this is a suspended object. Here we have a floating ship. Buoyant force is pushing back. Here the person, actually it's not suspended, it's not floating, it's resting on the bottom of the container, in this case the swimming pool or the lake. He feels buoyant force because of this displaced water. The rock feels buoyant force. So yeah, that's the idea of the buoyant force. Let's see what else we have. Okay, now I think you guys have some idea what the buoyant force means. Buoyant force comes from this displaced. Displaced means the water that leaves, giving space to the incoming object, right? It comes, buoyant force appears or occurs because of this displaced water. If you think about the volume of that water, volume of the water that displaces. So let's say we create a special kind of beaker. Let me redraw this. That's not a good diagram. Alright, let's say we have this special arrangement. Okay, this is how it looks like. So here's the beaker, and one side we have this little opening or a spout where we can collect water that comes out. So we can fill it up to this level, right? And then we have a small container over here to collect whatever water comes out. Okay, now here's the object that we're gonna immerse in water, submerge. It has some volume. Now we're gonna put it inside, so it's gonna look like this, same size. So some amount of water will displace, right? So we can collect it. So here's the water. Now you know that this volume is equals to the volume of this thing. So buoyant force comes from an equal volume of water or equal volume of liquid that displaced by the submerged object. You need to get this whole thing connected, okay? There's a couple of different things we are talking about. When you submerge something in a liquid, equal amount of volume has to displace, it has to give space to this thing. That volume is responsible for giving the buoyant force. Now here we can collect that into a container and measure it, but if a ship is in the ocean or a person is sitting inside water, there's nothing really coming out from the lake, right? The water level, the amount of the water level goes up. You really can't measure it. It will be nanometers, we don't know. But it displaces. It has to give space. And that water is pushing back and creating the buoyant force. Okay, so couple of centuries ago, a genius person named Archimedes saw this, studied this, and came up with this very important idea. We call it Archimedes principle. You might have heard the background story that he was given a task from the king to, this is the story what I have heard, to figure out whether the king's crown, whether it's real gold or whether it's mixed with something else. So Archimedes he's been thinking, and at some point he figured out a method. According to the story, he was in his bathtub. He didn't realize that he doesn't have clothes, got out of it and ran through the streets in Rome. I think he was in Rome. Shouting, "Eureka, Eureka!" That means I found it. So anyways, so what he found out, the experiments he did about this buoyancy and all that. So let's replicate it. So let me give you the Archimedes principle first. It says Archimedes principle. I'm not going to write the whole thing. Archimedes principle says the buoyant force on an object, immersed in a fluid, this is important. It doesn't need to be water. It's not just a liquid. It can be a gas also. So we can talk about like a hot air balloon in atmosphere. Atmosphere is the fluid. Hot air balloon is the object, right? So it doesn't need to be a liquid all the time. So the buoyant force on an object immersed in a fluid is equal to the weight of the fluid displaced by that object. Okay, this is called Archimedes principle, and you need to know this exactly word by word. So it's on the PowerPoint. It's in your textbook. You can Google it, but make sure that you know how to explain it. So this is Archimedes principle as it explained in a textbook. Now let's see what this thing really is. Let's look at the experiments Archimedes did. So he took this object, right, some object, and measured it using a scale. Let's say he measured the mass and also measured the weight, and he found out that it is let's say 10 newtons. Okay, and then he took this container of water, in this case let's use water, and he has this collection arrangement, and then he will immerse this into water. Now the scale reading decreases. Now let's say it reads 7 newtons, right? Outside water 10 newtons, inside water 7 newtons. So what's the difference? Difference is 10 minus 7 equals 3 newtons. Now this is the buoyant force. At the same time, when this object comes into the liquid, the water displays, right? So he collects the amount of water that comes out. So we know that the volume of this water is equal to the volume of the object. Now he takes this water out. He's gonna weigh it. So he has this weighing scale, like a kitchen scale. You can place the water container. So you take it, put it here. You're gonna weigh it. What do you think the answer is? Weight of the water is also 3 newtons. There is a weight difference in the object. That difference is same as the weight of the displaced water, right? So if you go back to the principle, the buoyant force on an object in a fluid is equal to the weight of the fluid displaced by that object. If you measure the weight, it's going to be same as the weight difference or the buoyant force of the object. So that's the whole idea of Archimedes' principle, which is very useful. So we're going to work on few problems. Alright. So spend some time, go back and forth and make sure that you understand this thing correctly and as much as you can. Okay, let's try an example. So I'm taking this example from the PowerPoint. It says a 70 kilogram ancient statue lies at the bottom of the sea. 70 kg ancient statue. So here's the bottom of the sea, here's the water level, and here's this. So let's say this is the statue. I can't draw as it looks like in the PowerPoint, so I'm going to draw it this way. So here's the statue. Can you recognize this statue? It's an ancient known figure. Alright, anyways, maybe now you give it a try, okay? If not, it's from a recent movie. Okay, moving on. 70 kilogram ancient statue lies at the bottom of the sea. Its volume, so volume is 3 times 10 to the 4 centimeter cubes. How much force is needed to lift it? Alright, so we have this expedition people, archaeologists here. They want to lift it, so they throw the rope, tie a knot, try to lift it. Now we know that if the statue was outside water, the force you need is simply mg. That will be 70 times 9.81. That's gonna be some 680 something. 70 times 9.81, 686.7 Newton. So this much force you need if outside water. Okay, but now this thing is inside the water. It will be little lighter. So let's calculate. So how do you find that? We need to know what the buoyant force is. How do you find that? Buoyant force is equals to the weight of the displaced liquid, in this case water. This is coming from the Archimedes principle, right? The buoyant force is equal to the weight of the displaced liquid. So what is the weight of the displaced liquid? How do you find that? Let's find what is the volume of displaced liquid. Volume is same as the volume of the statue, right? You have a statue of 3 times 10 to the 4 centimeter cube volume, so the liquid should have the same volume. So 3 times 10 to the 4 centimeter cubes. Now I'm going to convert this into meter cube before I do anything. How do I do that? 3 times 10 to the 4 multiply by or divide it by 100 3 times. 100, another 100, another 100. So 3 times 10 to the 4 times 10 to the 1, 2, 3, 4, negative 6. 3 times 10 to the negative 2 meter cube. That's the volume. So volume of the displaced liquid is 3 times 10 to the negative 2. Alright. What we need is weight of the displaced liquid. Weight of the displaced. So let's find the mass of displaced water or liquid. So we know that density is mass divided by volume, so therefore mass is density times volume. So this is density. We are talking about water, so density is 1000 multiplied by volume 3 times 10 to the negative 2. So now we get cancels out 2 zeros, we get 30 kilograms. Alright, weight of displaced water. 30 times 9.81 for 300 290. Let's see, 30 times 9.81 294 294.3 newtons. So what's the buoyant so this is the buoyant force, right? Weight of the displaced liquid equals buoyant force. So how much force do we need? Or in other words, what's the apparent weight? What is the weight these people in this ship gonna feel while it's inside water? So that apparent weight is the actual weight, 686.7 minus 294.3, which is equals to 392.4 newtons. So when they're pulling this up, this is the force they're going to feel, right? This is the weight they're going to feel. The moment it surfaces, when it comes above the water level, they're going to feel the actual weight of it. Until then, this is the weight they will feel. That's why we call it apparent weight. Okay? Alright. Okay, so let's move on. Okay, let me clear this. Couple of things, that some important points. Let's say here's water, and now if it is fresh water, we know density is 1000 kilograms per meter cubes. So anything denser than water, like something like this piece of rock, it sinks and it feels buoyant force, but the weight in this case, weight is bigger than buoyant force. Something like wood, piece of wood, it floats. In this case, you can't say that buoyant force is bigger than weight. That doesn't happen. Buoyant force will support up to the weight. So in this case, the entire weight is supported by EF, buoyant force. There is, it's not going to work the other way, like there's too much buoyant force, bigger than the weight. That means that's not real, right? So if something is floating, means the weight is completely supported by the buoyant force. Now floating can happen at different levels. Sometimes, okay, let's do a different object. Something can float like this. Most of the object is above the water, like a ship. So displacing this much water or the liquid is enough to create buoyant force to support the weight. So here's the weight. This volume which is underwater is enough to create that necessary buoyant force. If it is a heavier object, like if you put something on top of it, like imagine we have like a raft or a barge, something that floats, and then you load things into it. So the things will start go underwater, like it will go like this, right? So you have put some stuff on top of it, you have made it heavier, so it has to displace more water to create that extra buoyant force to support this whole thing. But still the weight is being supported by buoyant force. Sometimes things can float right by the surface, heavy object. Still buoyant force and weight is equal. In this case the entire volume needs to be displaced because you need more water to create more buoyant force. Alright, so there's different scenarios of floating. So another interesting question is the amount of volume. How much volume does it need to go underwater in order to float? So let's say something like this. My easiest example is having a cube or a rectangular cube kind of object. So let's say we have a raft, and let's say dimensions, once this side is 10 meters, this side is 2 meters, and this side let's make it 3 meters, this side is 2 meters. Okay, and let's say this is made out of some very light wood, so the density of it is 600 kilograms per meter cube. Now the question is, if you put it in water, where is the water level? So if you just draw the one side, it's gonna look like this. This is that 2 meter side, and here's the water level. It's floating. You can safely assume that it's 600, the density is 600, so it is lighter than, it's less than the density of water, so it will be floating. Question is, what is the water, where's the water level? Like for an example, what is this height? How do we do that? Let's first find the weight of the object. To find the weight, first we need to know the mass of the object. We know that mass is density times volume. So 600 multiplied by volume. It is it's a cubical shaped thing, so we multiply the sides. 10 times 3 times 2. So what do we have? 660 times 600, 3600. 6,000, 12,000, 6,000, 36,000, right? Let me do the math real quick using the calculator. This is embarrassing, but we do it. It's 3 times 2, yeah, 3,600 kilograms. That's the mass. So what's the weight? Is mg multiplied by 9.81 I have 35,316 newtons. 35,316 newtons. Alright, so that's the weight of the object. That means buoyant force has to match that 35,316 newtons. So that's the buoyant force. Buoyant force comes from the volume which is underwater. This is the amount of water that displaced. So the buoyant force comes from this volume. So buoyant force also is the weight of the liquid. Buoyant force is the weight of the liquid. So we have the weight of the liquid, weight of water. So I'm gonna write here. Okay, I'm sorry for writing all over the place, but BF is 353160. Weight of water is same, 353160. Mass of water. So if we have the weight, now we can find the mass. So we're going to divide it by 9.81. And you see it comes back to 3600. 36, it has to be, right? The two masses, if the weights are same, the mass has to be same. But we don't say that the same amount of mass being displaced. We say weight because that's the standard, that's the definition, kilograms. Okay, so what's the volume of water? How do you find that? We know that density is mass over volume, so therefore volume is mass over density. So this divided by this cancels, gives you 36 meter cube. Now this amount underwater, right, this line underwater is 36 meter cubes. So we know that this is also a rectangular cubical kind of piece. So if you have the volume, it comes from if we call it H, 10 times 3 times the two sides, this is 10, this is 3, and this underwater piece times H is 36. So H is 36 over 30. So what is 36 over 30? 1.2. 1.2 meters. 1.2 meters will be underwater. If somebody asks how much above the water, it will be 2 minus 1.2, right? 0.8. Okay, so yep, that's it. So there are other questions we can ask, like, okay, so if I say it is safe to load stuff on this. Now this is a raft, so you can load things on this. It is safe to load things all the way up to 1.5 meters is underwater. So how much mass you can load on this thing? So there is different kind of questions you can ask. Or what's the maximum you can load on this, so that it comes all the way, all that 2 meters goes underwater, like about to sink. What is the maximum you can load? Okay, so there's different variations we can do with this. Okay, I believe that's enough with Archimedes principle. The same type of questions we can ask with gases, like as I told you guys before, like a helium balloon in the atmosphere, how much weight it can lift, because the balloon has buoyant force from the surrounding atmosphere. It's going to get lifted because it's less denser. That's why we put helium in it, right? Helium is less denser than the atmosphere. or a hot air balloon. Helium, well, helium is kind of difficult to come by. So hot air, like you increase the temperature, the density of air gets smaller, so it increase the buoyant force. I mean, it get less denser, means it can float. The surrounding air can lift it. So we will discuss few questions next time when we meet. Okay. All right. Thank you, everybody.